The title of my talk is Electrochemistry Everywhere. Because it really is. We're going to see in the future, and we're already seeing it today, a dramatic growth in this field and its impact broadly on human society. So, what is electrochemistry? Electrochemistry is electricity driving chemical reactions, or vice versa, chemical reactions generating electricity. The latter is a technology you all know, batteries. But I'll spend tonight mostly talking about the former, how we use electricity to drive chemical reactions. So I'll begin, though, with a funny story about electrochemistry. Electrochemistry began with a frog. I'm serious. In the 18th century, there was an Italian scientist. His name was Luigi Galvani. You may have heard of the term galvanic. And he was interested in what caused animals to move. And he discovered, that if you took two wires and stuck them, attached them to a frog leg, a dead frog leg, it would twitch, it would move. He called this animal electricity. He thought the animal had some intrinsic power to cause this motion, and that this animal electricity that he had discovered was the key which gave organic matter life. But this was quite controversial, even at the time. Another Italian scientist, Alessandro Volta, realized an important fact. When Galvani made his measurement, he used two different metals. Now, as chemists, material scientists, we know that metals have electrons with different energies. And when you put two metals, like the orange and blue wires here, with different energies, and you connect them with a salt solution, the frog's leg in Galvani's case, you get a battery. Because one metal wants to give up its electrons, the orange wire here, and the other metal takes those electrons, in this case the blue wire. So when you connect these wires to a salt solution, which conducts electricity by moving ions, charged molecules, you get electrical current. When our muscles move in our body, it's triggered by an electrical signal, an electrochemical signal from our brain. And this current from these two probes actually was what stimulated the frog to move, the leg to twitch. So Volta, trying to in proving Galvani wrong, actually built the world's first real battery. And it looked like this. Stack of different metals with different electron energies, with sheets of paper between them, wetted with electrolyte solutions, salt and water. And it turns out this revolutionized the field of chemistry. So this is a picture from Humphrey Davy's laboratory in England, where he worked with his student Michael Faraday, names you might recognize, to use batteries like this to discover many elements for the first time. They used electricity to separate compounds found in nature into their elemental form. And this was, in many ways, the birth of modern chemistry. And it was all based on electrochemistry. So electrochemistry is incredibly important historically, but it's also important for the future. So let's imagine a world where we have all of our energy coming from renewable sources, intermittent sources, wind, solar, hydro for baseload, are producing our electricity. But making electricity renewable will only address about a quarter of our carbon dioxide emissions. We need ways to use our renewable electricity for manufactured products, building materials, transportation, agriculture, if we're to become a carbon neutral society. So electrochemistry is in fact the interface between clean, renewable electricity and all of the other things we need to run our civilization. For example, we'd like to use electrochemistry for production of steel, cement used in construction. We'd like to use it to make chemicals and polymers in consumer products. And of course, you hear a lot about batteries these days. You're seeing them all over the place. In electric vehicles, we still need less expensive, lighter batteries. But we also need massive grid-scale energy storage to completely get off fossil fuels because renewable electricity is intermittent. New electrochemical technologies are part of that solution. And although batteries, they serve us quite well for cars, they're not well suited for larger scale transport. They're simply too heavy. The physics doesn't work for planes, ships crossing the Atlantic or Pacific. For this type of transportation, we need synthetic fuels like hydrogen. And this is something that we're very excited about. You can fly a jumbo jet with liquid hydrogen, but the engineering must be done. We also need these cargo ships that cross the Pacific or Atlantic. You can't do that with a battery. You can do it with hydrogen. For these, we need to make hydrogen not from fossil fuels, but from renewable electricity. And this is something that I'll touch on tonight. Electrochemistry is more than that, though. It's also the data link between electronic devices and living worlds. Our brain, our neurons, are electrochemical systems. And any human interface to the brain involves electrodes and electrochemical processes. Semiconductor technology that's in your smartphones uses electrochemistry to build and pattern and grow metals in 3 dimensions at the nanometer length scale that connect the circuits together. I won't talk more about these applications, but I want to make the case, impress upon you, the importance that this field of electrochemistry is to many aspects of our life. Now I'd like to talk a little bit about some of the science we've been doing, some of the advances we've made that led to the still, to me, quite remarkable fact that I won this incredible Blavatnik Award. So the first is about the production of hydrogen. As I mentioned, hydrogen is a key component to decarbonization. If we cannot produce it at scale, we are unlikely to solve many of our decarbonization problems. And establishing the production and infrastructure for hydrogen is a major focus of US national laboratories. The Department of Energy has launched an Earthshot program with the goal of producing 1 kilogram of hydrogen for $1 within 1 decade. This is something we're very serious about. The process by which we produce hydrogen is called electrolysis. And I want to walk you through how we do this reaction, very simple terms, because it's a good representation of the types of processes we think about. Electrolysis is the process by which we take water molecules, H2O, here oxygen in red and hydrogen in white, and we split them to form H2, hydrogen gas, and oxygen gas, O2, as you see on the right. But water is stable on its own, of course. So we have to use electrical energy to drive this chemical reaction forward. We use what is called an electrolyzer. It's a closed cell into which we pump water, and oxygen and hydrogen gas comes out. Inside the cell is a membrane or separator that allows ions to move, to carry electronic current inside the cell, like the frog's leg at the start of the presentation, but keeps the hydrogen gas and the oxygen gas apart. You don't want them to combine and explode. To run the reaction, we put in 2 electrodes, a positive in orange and a negative in blue here. We connect these to a power source, and the membrane between them only lets the ions pass. Now, electrolyzers, of course, they're not a new technology. But the best commercial technology of today now relies on expensive and potentially environmentally harmful materials. The shell of the electrolyzer is made of titanium. The electrodes of these electrolyzers are iridium, platinum. And because the membrane itself is a very strong acid, these materials are rare and expensive. The membranes are fluorocarbons, which are the forever chemicals we just heard about. Former Laureate Will Dechtel's technology is developed. It's certainly good at removing these from the environment, but we would much rather not put them there in the first place. So our work has been focused on finding new ways of performing this electrolysis reaction with cheaper, greener materials and making them commercially viable. And we've made some good progress. Our new electrolyzer design has a shell made of cheap steel, electrodes from iron, cobalt, nickel, and a membrane from simpler plastics, hydrocarbons, that are less harmful for the environment when they degrade. And while simple in principle, the real-world complexity of these engineered electrochemical systems making all these changes and getting the performance and durability we need challenging. Now I want to take you inside the electrolyzer and highlight the discoveries that are enabling now these new technologies. So the reaction starts by flowing water in, and the water reacts at the negative electrode, which creates hydroxide ions. That is, water missing one hydrogen. And those hydrogens pair up to form molecular hydrogen gas. The reaction continues with hydroxide ions flowing across the membrane, where they react with each other to create oxygen, some water, and release electrons onto the positive electrode. This completes the cycle. And if we can do this, as we can now with cheaper, more accessible, and more environmentally friendly materials, we can make a disruptive hydrogen technology that dramatically lowers cost. The key to this development is understanding how these reactions work at these inexpensive electrodes with tremendous detail, molecular detail, and iterating through that understanding a design that leads to better performance. In particular, finding, understanding, and improving the material at the positive electrode, the electrode making oxygen, was really critical. The fastest catalyst we found for this reaction has atomic layers of iron, nickel, and oxygen, shown here on the right. And we analyzed the behavior of materials like this, from the atomic scale to the nanoscale. Here in this movie, you can see an individual layer breaking up. The atoms of nickel and iron are moving around as the reaction is catalyzed. And we understand this also all the way at the device level, the microscale. Here you see a cross-section of our electrode where the catalysts are these white flakes on this metallic support. And so this understanding, this sort of multi-scale understanding of how the material behaves, both in carefully controlled model systems all the way to real-world operating conditions across length scales, allows us to iteratively design and improve these devices. So to summarize this part, we took a technology for hydrogen production. Right now it's expensive, possibly harmful to the environment. We've been working to replace it with a technology that uses inexpensive and accessible materials. We're working very hard with our industry partners to try to bring some of these innovations to commercialization. The second topic I want to talk about is how we're driving innovation with both basic science and device work towards carbon dioxide capture. New ways to take emitted carbon dioxide out of the air, out of the ocean, or from fossil fuel emissions at large point sources. So as with hydrogen production, this is something we can do already. So here's a picture of a facility. I was able to visit Carbon Engineering there in Canada. They take carbon dioxide out of the atmosphere right now at a pilot scale using potassium hydroxide and convert it to potassium carbonate. Potassium carbonate is a salt, not one you would want to season your food with, but one that can be used to lock away carbon dioxide. While we can do this already, the process must be a lot more efficient and much lower cost to scale and truly impact our lives. Now, this is a more complicated reaction, and thus it requires a more complicated device than for the hydrogen electrolysis. But the general principle remains the same. We drive a chemical reaction by applying electrical current and inducing the flow of ions through membranes. So the key development we made in our lab, shown in the middle, is called a bipolar membrane. This membrane dissociates water, H2O, into hydroxide and hydrogen ions and directs them in opposite directions. This process was a key limiting step in the larger reaction, capturing carbon dioxide using the hydroxide. And when we perform this reaction with salt water as an input, we create an acid like hydrochloric acid and a base like potassium hydroxide, which we can then use to capture carbon dioxide. And bipolar membranes like this already exist, and in fact, they're actually used in the wine industry, the wine you're drinking, to adjust the acidity of wine. but they're not nearly efficient enough to capture carbon at scale. And so what our lab has managed to do is to understand how this water is dissociated on the surface of materials in this bipolar membrane, and then use that understanding to design new catalysts to dissociate the water for the very first time. And the membranes we developed now dissociate water with 50 times lower energy loss than the commercial state-of-the-art. We're excited about taking this technology, this more efficient technology, and applying it to taking carbon dioxide out of the environment. And our discoveries are really leading an explosion of research, both on devices and fundamental science and bipolar membranes. And we're working also very hard to commercialize this technology, to move beyond narrow applications and to the large-scale capture of carbon. So that's just a small sample of what we're working on at the University of Oregon. And because of the scale and complexity of the problems we're trying to address, here we're using electrochemistry for energy and ultimately addressing climate change. We've had to think really hard about how to best organize our efforts for impact. And one thing I'm very proud of is to say that we've established the premier center for electrochemistry that tries to really address the full scope of that challenge. Not only do we do this fundamental science, but we've also built a first-of-its-kind education program that's putting 20 or 30 students a year into workforce, building industry partnerships, doing also the applied R&D that's inspired by our basic science, and contributing sound techno-economics to policy by connecting with our local policymakers, with our utilities, the local utilities. So building the Center for Electrochemistry has been fruitful, amazing experience, but it's also made me face some of the barriers in academia and think critically about what are our goals, what is our purpose, and what is the best structure of a modern research university. And with that, I want to thank you all for your attention, and particularly to Mr. Len Blavatnik. Thank you, Len. I really appreciate this, truly. The Blavatnik Family Foundation and the New York Academy of Sciences for this tremendous honor. Thank you so much.